This lecture aims to introduce you to the topic of time complexity. Here is the roadmap of what we will cover. In this lecture, we will introduce you to the concept of time complexity and provide a definition for different terms such as algorithm, random access machine model, and time complexity. So why do we need to study time complexity? Or say why does it matter? Think about how many searches you would do via Google on a daily basis. Every query could potentially lead to hundreds of thousands of results, and they all need to be ranked by relevance. Ordering so many results for one search is expensive. By saying that, I mean it takes time and computational resources to do this task accordingly, even for one search. Now think about how many searches are handled by Google on a daily basis, given the large number of users. The same thing can be said for any other computational tasks. As a result, we always seek more efficient algorithms that take less resources and less time to get things done. How do we measure the efficiency of an algorithm? That's what time complexity does, and why we need to learn a bit about it. Before we introduce you to the formal definition of time complexity, let's start with a simple question. How do we measure the efficiency of code? To be specific, we can ask this question a different way. How do we measure the speed of a given function or method? To answer this question, you can think of a few options. For example, you may think like this. Can we use the actual time it takes to run the function or methods? If you do so, the measurement may not be exactly fair, depending on where you are running the code. If you aim to compare the efficiency of two algorithms A and B, but you have A run on a personal laptop and B on a cluster of supercomputers, the actual time it takes to run those two algorithms may not fairly reflect which one is faster, because the setup is already skewed. That said, the actual time it takes to run the function or methods may not be a great measurement of the efficiency of the code. Then you may be thinking, how about the steps it takes to execute the function or method? Well, let's use an example to figure that out. Here on the screen, you can find the algorithm that searches for the max value given a linear data structure, like an array. It uses a variable named result to contain what's eventually returned. It starts by picking up the first element in the array, and then traverses through the whole array and compare to see if there's a bigger element. If there is, then we put that element's value inside the result variable. In the end, the result is returned. If the input array size is 1, roughly 4 steps are executed. Assigning the first element to the result variable, the if condition in the for loop, as well as the statement underneath the if condition. Lastly, the returning statement, of course. So because we are only doing an estimate, so we won't bother figuring out which line of code actually gets executed or not underneath the for loops. Let's just roughly estimate that, so we can count that as 1, 2, 3, 4, 4 steps being executed. When you have an array with 3 elements, it will take about 8 steps to execute the function. The for loop runs for the same number of times as the input size, which is 3, but there are 2 steps underneath it, assuming that both would get executed, so you would have 3 multiplied by 2, which gives you 6 steps. Don't forget that there is the initial step that assigning the value to the result variable, as well as the last step to return the result. So you need to plus 1 and another 1. That will give you 8 steps in total. Again, that's a rough estimate. We won't bother to figure out which line underneath the for loop really gets executed. Similarly, when you have an array with n elements, it will take 1 plus 2 multiplied by n plus 1 steps to execute the function. As you can see, different input size will lead to different numbers of steps to be executed. Which one of these is really representative of the speed of the function? If you account for the varied input size and ask yourself this updated question, how about the steps it takes to execute the function or method in relation to the input size? It will become a better measurement of the function speed. Let's use the same example we saw earlier to make sense of it. Well, the same function, find max, that searches for the max value given a linear data structure. To account for the varied input sizes, we will use Tn as a function to stand for the speed of the function, where n is the size of the input. It can be any positive integer, say 100 or 2000. Regardless of the size of the input, we know that the first line of this function will always be executed. I mean, the assignment of the first element to the result variable will always be executed. That's one step. If we just want an estimate, we can assume that both the if condition and the statement underneath the condition will be executed, which makes two steps. The for loop runs for n times, same as the input size. In the end, the return statement is always executed. So that will give us 2 multiplied by n plus 2 steps in total. In summary, the way that we measure time complexity of a given function or method depends on the input size, and is typically expressed as a function in relation to the input size, which is a better measurement than just the actual time it takes to run the code, and also better than the steps it takes to execute a function, because it fails to account for the varied input sizes. That said, this is everything about an informal introduction to what time complexity is. Now let's introduce you to the formal definition of time complexity. Before we do that, we need to start by defining what algorithm is first. So what's algorithm? An algorithm is defined as a finite procedure that takes an input and produces an output. It's an effective method to solve problems, typically. An example of algorithm can be the findMax function that we examined before. It's a finite procedure that takes a linear data structure like arrays as the input and produces the identified max value as the output. So formally speaking, we will use random access machine model to analyze the efficiency of algorithms. The random access machine model, short for RAM model, is a theoretical model of computation, and it assumes a simplified, idealized version of computer system that processes instructions sequentially. The RAM model has a few key features or say assumptions that will be very important when it comes to analyzing the time complexity of a given algorithm, such as the computer has infinite amount of memory. Each access to memory location, or say read and write, takes constant time. This is actually on the input or say the output operations. Basic arithmetic operations like plus minus, logical operators like and or, comparisons like bigger than or smaller than take constant time. Executing a single instruction such as assignment, branching, or looping takes constant time. The time complexity of an algorithm is determined by counting the number of basic operations it performs. Of course, this is based on the assumption that input size has already been accounted for. So based on such assumptions, let's try to analyze the time complexity of a given algorithm example. Again, we will stick to something similar to the findMax we saw earlier. Well, it's still findMax. So what you can see on the screen is the pseudocode of the findMax, along with the line numbers at the right side. The input is still an array. The first step assigns the first element to the variable y, which is the first line. The second line starts the for loop. Under the for loop, you have two steps, an if condition and its statement, corresponding to lines 3 and 4. The if condition checks the value of y against every other element in the input array as you traverse it. If the current element is bigger than y, then you will assign its value to 1. In the end, you return y, which is step 5. From the RAM model, we learned that the steps such as assigning a value to a variable, or returning a value, or comparison all take constant time. To simplify things, we are going to mark all those things as taking a single step to execute. So line 1 and line 5 both take 1 step. The for loop runs for n steps, which is the size of the input array. Under the for loop, the two lines, the if condition and its statement, take 2 steps, depending on if the if condition is being met. As you can see, the different input may lead to algorithm taking different number of steps to execute. So what characteristic should the input array have for the algorithm to take the least number of steps or the most number of steps to get executed? If you try a few examples, you will see that the key difference lies in whether both steps 3 and 4 are both executed or only step 3 gets executed. The best scenario, or say the best case, is when only step 3 is executed. That literally saves us 1 step underneath the for loop, because the for loop runs for n times, which is the size of the input array. That could potentially save us n steps in total. Okay, so the best case only happens when the input array is in descending order. In that case, the if condition will never be met, because A is initially assigned of the value of the first element in the array, that's the biggest element in the array. So the if condition would never be met, and the statement underneath the if condition would never get a chance to get executed. The worst case is when both steps 3 and 4 are always executed, and that only happens when the input array is in ascending order. In that case, the if condition is always met because A is initially assigned the smallest element in the array. As you traverse the whole array, every new element you encounter will be bigger than the current value of A. So both the if condition and the statement underneath the condition would be executed. Okay? So from our informal introduction of time complexity, we know that the time complexity Tn is expressed as a function in relation to the input size n. This is the same when RAM model is applied. So you can compute the Tn for both the best case and the worst case accordingly. For the best case, because only step 3 is executed, you can calculate Tn as n plus 2. Where does the 2 come from? 2 comes from the initial assignment of the first element to the variable y, and the returning of the y variable in the end. So for the worst case, the only thing that would change is that you need to multiply n by 2, because both steps 3 and 4 are getting executed in every iteration of the for loop. Beyond the best and worst cases, you can estimate an average case that sits in between. If you plot the best and the worst cases in a 2D plane, the average case will sit somewhere in between. You may notice that we have simplified our estimate of time complexity by assuming that each step takes just 1 step, except for the loop. It's not exactly what the RAM model says. The RAM model says that the simple operations such as assigning a value to a variable or returning something, all these basic operations take constant time. Okay, constant time. That's why you're likely to see a different set of notations like C1, C2, or C3 in a lot of textbooks. C is short for constant, and they all stand for constant times. If you stick to the same notations and strictly follow the RAM model, it will express the time complexity for the best and worst case differently, basically replacing all those ones with constant time symbols like C1 or C2. Okay, for the best case, Tn will be expressed as C1 plus n multiplied by C4 plus C5. So here C1, C4, and C5, they all correspond to the line 1, 4, and 5, and they stand for constant numbers. Similarly, for the worst case, Tn will be expressed as C1 plus n multiplied by C3 plus C4. In the end, we would plus C5. You may think that, well, here all these C1, C4, C5, they are just some constant numbers. Maybe we can somehow simplify them. For example, in the best case, you have C1 plus C5. Could we replace that with just a single symbol instead of two? Yes, you can. Actually, it's very common to replace multiple constant number symbols with a single symbol, like using D to replace C4 plus C5 in the best case, or using C subtext B to replace C3 and C4 in the worst case. Okay, so both C subtext A, C subtext B, or D, they all stand for constant numbers. So using single symbols to represent constant numbers make it easier for us to see the nature of the time complexity functions. In our case, both the functions in the best case and the worst case are just the linear functions. So far, we keep using the phrases like best case or worst case, but we have never really defined them formally yet. Well, to summarize from this example, the best case is when you have some input that leads to an algorithm to take the minimum number of steps to run. Okay? The worst case is when you have some input that leads to the algorithm to take the maximum number of steps to run. It's rare for the best case or worst case to happen given a random input. So that's what average case comes into play. The average case is the estimate of the algorithm to run given arbitrary input. It's typically sitting between the best and the worst cases. Now you have a basic understanding of time complexity. The next step is to make sense of all these via a concrete example. In the next video, we will dive into the insertion sort, using that as an example to help you make sense of the time complexity further.